A very good morning to all of you. Now, today we are going to understand one more important topic, that is biostabilization and the stability factor. Now, you know that the transistor should be operated in the active region for the amplification, and for the faithful amplification, the operating point of the transistor should be selected at the middle of the DC load line. Only then you will get the faithful amplification, otherwise not. Because if you have selected the operating point near to the cutoff and the saturation region, then in that case the waveforms of the IC and the VCE will be clipped off. But this IC depends upon some factors, and because of that there is a requirement of the stabilization. Now you can see that the IC depends upon the beta into IB plus 1 plus beta into ICBO. Now this is the equation of the collector current for the common emitter configuration. You can also write this 1 plus beta into ICBO as ICEO. So you can see from this equation the IC depends upon the beta and the ICBO. Now, what and how that this beta is going to vary the IC. Now, suppose if you are going to replace your transistor in the circuit, then the beta is going to vary. The beta will be having different values for a different transistor. Even if you take the same type of transistor, the beta is going to vary. It means that if beta varies, then the IC is also varying. So IC will either shift upward or it will shift downward, and in that case your operating point is going to be unstabilized. Now similarly, you can see that this ICVO, it depends upon the light intensity and the temperature, because ICBO is the minority current and it is due to the minority charge carriers. So you know that when you are going to incident the light of the higher intensity, or when you increase the temperature, the ICBO is going to increase because the minority charge carriers increases. So when ICBO increases, so what is going to happen? Your collector current is going to increase. Now, for every 10 degree Celsius rise in temperature, the ICBO gets doubled. So if you increase the temperature to 20 degrees Celsius, then it will become 4 times. Now similarly for 30 degrees Celsius, and it will become 8 times. So if you are increasing the light intensity, it will be having the effect over your ICBO, and that is going to vary your IC. So when the IC varies, so what is going to happen? You can see here from this waveform. Now, when the IC increase, so there will be a shift in the operating point. You can see here when the IC is going to increase, so what is going to happen? So there will be a shifting in the operating point. Now, this operating point is going to approach towards the saturation region, or if it is going downwards, then it will be approaching the cutoff region. So in both these cases, your waveform will be clipped off like this. We have already studied this. So it means that there is a requirement of the stabilization. Now there is also one more important fact, that when you are going to increase the temperature, the VBE decreases. What is VBE? Now VBE is the base emitter voltage. So for every 1 degree Celsius rise in temperature, the VBE decreases by 2.5 millivolt. So because of this temperature and because of the transistor parameter, there is a requirement to stabilize the operating point. As you know that for the faithful amplification, you will have to keep your operating point continuously at the middle of the DC load line, because our main aim is to amplify the AC input signal which you are applying at the base of the transistor in the common emitter configuration. So in that case, there is a high requirement of the stabilization. So now we will be having we will be having the stability factor. Now, what is the stability factor? Now, stability factor is also explained as the rate of change of collector current with respect to the ICPO. It means that how the collector current changes with the change in the ICBO. So we can say that if the value of the stability factor is lower, then the system will be more stable. Now these are the S prime, that is the rate of change of collector current with respect to VBE, and the S double prime will be the rate of change of collector current with respect to beta. So we can conclude that when the value of S prime and the S double prime are small, then the system will be more stable. We want our IC to be independent of ICBO, VBE and beta. We do not want that if you are changing the ICBO, then it will increase or decrease the IC. In that case, your operating point will shift upward and it will shift downward, and that will cause the problem in the amplification. So, the lower the value of S, that is the stability factor, then the system will be more stable. So now we are going to see some biasing circuit which is required for the transistor biasing. Now the first requirement for this biasing circuit is to select the operating point, and the operating point is always selected at the middle of the DC load line. So why you will have to select your operating point at the middle of the DC line? The only requirement, the only purpose is that we want a faithful amplification. Then you will have to stabilize your IC against the temperature variations, because if the temperature varies, then it will vary your ICPO, and that is going to vary your IC also. And IC should be free from the transistor parameter also. Now what is transistor parameter? Transistor parameter is a beta. So first circuit which we are going to analyze is the fixed bias circuit. Now this is also called a base bias circuit. So why it is so? Because you have connected a resistance between the input battery and your base terminal. So now in this fixed bias circuit, you are having two different sources, that is VBB and the VCC. VBB is applied to power your input port and VCC is applied to power the output port. Now this will make your base to emitter junction forward biased, and this VCC is going to make your collector to emitter junction reverse biased. Now you can see the terminals are same only, so why not to have a single battery for this fixed bias circuit? Because if you are going to use the two batteries, then it is going to increase the cost of your system. So instead of having these two batteries, if we can replace these two batteries by a single one, then it will economize the circuit. So in that case, what you will have to do, just you will have to take the 180 degree of it. So you can draw this circuit as in this fashion also. So we are not changing the circuit, we are just simply modifying it. Now you can draw the circuit in this fashion also. If you are taking the 180 degree version of this, then how it will look like? It will look like this. You are having a battery also. See, you are having a battery. Okay, I'll draw here for a better understanding. This is a simple transistor. Then a resistor will be there, that is RB. Then the positive terminal will come. Then the negative terminal, this will be your VBB, and this way. Then after this, there is a ground. So this is our first battery. So now you will have to draw the second battery. So this one is your RC, and again if you take the 180 degree phase shift of this battery, so then the positive will come here, then the negative. So in this battery you have taken two cells, and then the ground will be there. So now this is the modified version of the fixed bias circuit. Now you can see here we can replace these two batteries by a single one. In that case, you will have to use only a single battery. It means that your RB will be connected to here. Your RB will be connected. So we have not done anything. We have just taken a single battery instead of two. So now for a better understanding, you can just go through this picture. See, so now you are having two resistances, that is RB and the RC, and this single battery is sufficient enough to make your base emitter junction as the forward biased and the collector emitter junction as the reverse biased. So when you are applying the voltage, the current is going to flow through this. The current is going to flow through this RB and the RC. Now, the current which is flowing through the RB can be termed as IB, and this one will be IC. So now you are going to have some voltage across base and the emitter, and that voltage will be 0.7 volt because we have to forward bias the base emitter junction. So 0.7 volt will be sufficient to forward bias your base emitter junction of the silicon transistor, and for germanium it is 0.3 volt. So now we will try to analyze this circuit, that how this circuit is going to operate when the variations will come into a picture. So now this is the final circuit of the fixed bias circuit. Now for this fixed bias circuit, we will try to find out the operating point. So operating point, if you want to find, then you need to find the two variables, that is IC and the VCE, because the DC load line is on the output characteristics of the transistor, and output characteristics is plotted between the collector current and the collector to emitter voltage. So now to find the operating point, it means that you will have to apply the KVL at the input port and the KVL at the output port. So when you are applying the KVL at the input port, so what is going to happen? So this is the complete circuit from the battery to the ground. We have to apply the KVL. So generally, you can see you can replace this circle by this battery terminals. So this one is positive and the negative. So we are tracing from negative to the positive. So it means that if you are going from minus to positive, then minus VCC will be there, then plus IB into RB will be there, and this is plus VBE. Because if the current enters into the resistance, then the positive will come here because the current is entering into that passive element, and then the negative. So we are moving from positive to negative. It means that there is a voltage drop. So for the voltage drop, I always take positive, then the plus minus VBE. So again, you are moving from positive to negative. So that is 0. So now from this equation, you can simply calculate IB. So IB will be equals to VCC minus VBE upon RB. So in this way, you can apply the KVL at the input port. So, but our main aim is to find the IC. Now, how you are going to find the IC? Now, you know that from this equation, what we have obtained, we have obtained IB equals to VCC minus VBE upon RP, but this VBE value is very small as compared to the VCC, because VCC will be in 10 volt, 9 volt. So as compared to 9 volt, the 0.7 volt is negligible. So we can write IB is nearly equals to VCC upon RB. So now you can see here VCC is having the constant value. We are not going to change the VCC value, and once the circuit is designed, the RB is fixed. So you are having the fixed value of the IB. Now that is why this circuit is a fixed bias circuit. Why? Because all the parameters in this circuit are having the fixed value, and because of that the circuit is called a fixed bias circuit. Now now to find the operating point, that is to find the IC, so we are having IC will be equals to beta IB plus 1 plus beta into ICBO. Now you can simply write this 1 plus beta ICBO as ICEO, because this ICBO was in the common base configuration. But when you multiply 1 plus beta with ICBO, then ICEO will come into a picture. But this ICBO and ICEO, these are very small as compared to the mean current. You can see here that is beta into IB. IB is a current due to the majority charge carriers, and this current is due to the minority charge carriers. So you can simply neglect this ICEO. So when you are going to neglect this ICEO, in that case IC is nearly equals to beta into IB. So we have already found the equation of IB from this. So you can directly write the IB value from the equation number 1, which we have already found out by applying the KVL in the input port. So this is the value of the IC. So we have found the first operating point. Now, what about the VCE? That is the second point. So if you want to find the VCE, then again you will have to apply the KVL in the output port. So we'll be going towards our circuit, that is the modified circuit. So now in this case, if you are going to apply the KVL, then again you replace this by this. So minus and positive. So minus VCC, then again the current is going to enter into the passive element, and that is the RC. So plus will be here and negative. So plus into IC into RC. So now in this case this will be plus and minus. So VCE will be there. So you can simply write VCE. So VCE will be equals to VCC minus IC into RC. So in this way you can easily find the VCE value. So now we will go move towards our operating point. So now we have calculated the VCE will be equals to VCC minus IC into RB. Now you can see from these two equations, your all the values are the constant. You see the beta, you see this IC will be equals to beta VCC minus VBE upon RB. So we have ensured that the operating point will be at the middle of the DC load line, because IB is constant. It means IC will be constant, and when the IC will be constant, your circuit will be stabilized. But the problem is of the temperature again. So what is going to happen? You see here when the temperature increases. So when the temperature increases, what will increase? Your minority charge carriers will be increased. So minority carriers is going to increase with the incident of the light. Then when the minority carriers increases, it means that the ICBO increases. Now you can see from the equation, ICBO increases, then what will increase? Then the collector is going to increase, collector current is going to increase. And when there will be a collector current, you can see from the circuit, the collector current was flowing through the RC. So IC will come in contact with the RC. So when IC will be entering into IC, so RC, there will be a heat loss, and because of that again a temperature increases. So again this cycle will repeat. Then again temperature increases, minority charge carrier increases, ICBO increases, IC increases, and again it will increase the heat loss further. So again there will be a further increase in the temperature, and this cycle goes on, goes on, goes on. So this is a cumulative process, or you can say a vicious circle. And because of that there will be enormous amount of heat which will get developed in the transistor, and because of that there will be a thermal run away. So in that case your transistor might get damaged. So we will have to prevent this thermal runaway condition. And so now how this condition is arriving? Now this condition is arriving because of the ICBO. So you can see here this thermal runaway condition is occurring because of the ICBO. Now similarly you can see IC will be equals to beta into IB. You can simply see from this equation. Simply you can see from this equation, that is IC will be equals to beta. So if you replace your transistor from the circuit, then what is going to happen? IC will increase. So there is no stabilization of the IC as far as this circuit is concerned. If you are changing ICBO, your IC is increasing. If you are changing the beta value, your IC is again increasing. So therefore there is a need, and you can say therefore there is an extreme need to modify this circuit, that is a fixed bias circuit. The only thing which is coming in favor of this fixed bias circuit, that this circuit is very simple to analyze, and you can see that the IB value is having the fixed value. You can say IB is having the fixed value, and because of that IC having the fixed value. But the thing is that the entire problem coming into a picture because of the ICBO and the beta. So this is not a stabilized circuit. Now we'll try to solve one problem on the fixed bias circuit. So in this problem, what is given? You see a simple common emitter configuration is given, and the RB is connected to the VCC and RC is connected to the VCC. It means that this is a fixed bias circuit. This VCC is powering both input and the output port, and you will have to find the operating point. So when someone asks you to find the operating point, so IC and the VCE will come into your picture. Now in this case VBE not given, then you can simply assume the silicon transistor. So when you are going to assume a silicon transistor, it means VBE will be equal to 0.7. Now how to find this? So to find this, simply you apply the KVL in the input port and you apply the KVL in the output port. So when you are applying the KVL in the input port, then again minus VCC, because you can replace a single circle, small circle, by this terminal, that is minus to plus. Then again you are having plus to minus, so minus VCC, right, minus VCC plus IB into RB plus VBE. So IB will be equals to, now if you do some modification, if you do some maths, then IB will be equal to VCC minus VCC minus, you can say, VBE upon RB. Now IB value will be equal to VCC. Now if you want to put 0.7, it's not a big problem, you can always put. So IB will be equal to 30 microampere. Now what is the IC value? So IC value will be equals to IC value will be equals to beta into IB plus 1 plus beta into ICBO. Now this term is very very small and it can be easily neglected. Now IC will be equals nearly equals to beta into IB. You already found out this IB value. So just put this IB value here, and the beta is given in the problem, that is 50. So IC is coming out to be 1.5 milliampere for this circuit. So you can simply note the IC value. Now, if you want to find the VCE, so how to find the VCE? So just apply the KVL here again. So that will be minus VCC. Then the current is entering, so plus and minus. So plus into IC into RC and plus VCC plus VCE. So this will be VCE will be equal to VCC minus IC into RC. The VCC value is given, then you are having the IC value you have just calculated. So you can simply calculate the VCE value. You just have to apply the KVL in the input and the output port. So to find the IC, apply KVL here. That is, the current direction will be from this point to this value. This is the closed circuit, and to find the VCE you apply a KVL here. So this is the only trick you will have to follow to calculate IC and the VCE. So now the value which is coming out to be, that is VCE, will be equals to 6 volt. So now again we will take one more circuit to explain this fixed bias circuit. So now in the amplifier circuit shown, the value of R1 and R2 are such that the transistor is operating at VCE equal to 3 volt, IC will be equals to 1.5 milliampere, when beta will be equals to 150. So for a transistor with beta 200, calculate the operating point. So now in this question, there are two parts. First, the beta is equals to 150. Then they have changed the transistor parameter from beta, and then we will have to see whether when you change the beta value how your IC is changing, because our sole aim is what? Our sole aim is to stabilize the operating point, and to stabilize the operating point you will have to maintain the IC and the VC at a constant value, but this is not happening in the fixed bias circuit. Now you can see in this circuit the capacitor is given to you. The capacitor at the input side and the capacitor at the output side. Now why this capacitor is important? So capacitor is going to block the DC. Suppose if you are applying any input signal, and if that input signal is having the DC, then this capacitor will be blocking that DC, and it will allow the input signal, that we can say AC input signal, to pass through it. So now you are having the input signal here and it is free from the DC. This is the only purpose of this coupling capacitor. So this coupling capacitor is normally used for the amplification. Otherwise, your DC will enter into your circuit and it is going to offset your amplified signal, and you will not get the proper amplification. So if you are going to find the operating point, so in that case you will have to do the DC analysis. So when you are doing the DC analysis, this capacitor can be removed, because now there is no interference of any AC signal. We are not focusing our circuit for the AC signal. We are doing a simple DC analysis, and in that case your capacitor will be redundant. They will not be having any significance. So this will be your circuit for the DC analysis. Now you can see that this circuit is similar to your fixed bias circuit, because R1 is connected to the VCC and this R1 is near to the input port, and similarly R2 is connected to the VCC and this is the resistance of the output port. So now you simply apply the KVL here and KVL here. So in that case, you are going to find the value because you can see here IC will be equals to 1.5 milliampere. The IC value is given to you, that is 1.5 milliampere. Now the current which is flowing through the R1 is IB value. Now how to find the IB value? So we are having one equation, that is IC will be equals to beta into IB. So IB will be equals to IC upon beta. So IC means 1.5 milliampere and you are having the current gain as 150. So you can simply evaluate the base current value. So now after evaluating the base current value, now you can have the voltages and the current. So you can simply find the resistance, that is R1. So now we can see here after applying, now we have done some mathematics here. So in this case, VCC minus IB into R1 minus VBE. So simply R1 will be equal, because we have to find the R1 and R2 for beta equals to 150 value. So R1 will be equal to 6 minus 0.7. This we have already explained in this case. So you can have this IB value as 10 microampere. IB will be equals to, just now we have seen, and then put the value here. So R1 will be equals to 530 kilo ohm. Now you just apply the KVL in the output section, and then it will come out to, and then R2 will come out to be 2 kilo ohms. So now we will try to understand the second part. Now we have replaced our transistor. Why? Because beta has changed. Beta has changed from 150 to 200. You can see here beta has changed. R1 and R2 will be fixed. We have not taken out the resistances. We have just taken out, we have just replaced the transistor with another transistor. We have actually bought a new transistor from the market and we have replaced that. Now for that beta equals to 200, you will have to find the IC and the VCE. Again, this is very simple. You just have to apply the KVL in the input port and the KVL in the output port, and that will solve your purpose. Now you can see here simply R1 we have just calculated from the first part, R2 is also calculated. So you can simply have the KVL in the input port, that is VCC minus IBR1 minus VBE. So you can have the IB value, then you can see the IC value will be there. And if you apply the KVL in the output port, so VCE value will be evaluated. So in this way, you can find the collector current and the collector to emitter voltage, which is the operating point for the transistor. So this is all about the fixed bias circuit. So if you have any queries, you can always ask me. Thanks a lot for today.